Another DraftScience video presentation and such. So this is a video too, this Applied Science guy. I don't think he'll ever respond to me. Maybe I'll try emailing him again or something. Very likable. I like most of his science, but I think he sort of evades the question, the elephant in the room in this video on kinetic energy and momentum. He's really not going to explain either one of them, and the illustrations he's going to use are not too good and blah blah blah. So I think there's lots to argue here, and I think his is a sincere effort to explain. I just don't think he goes into it with enough mechanical explanation. There's no mechanical explanation. Bye. Oh, okay, starting over.
Would impart momentum and cause them to spin the other way than they actually do.
Right, so he's talking about the, whatever you call it, the little thing that spins when you shine light on it, and the complexity of the physics, and the fact that it doesn't work in a complete vacuum, it only works in a partial vacuum, because what's happening is sort of deceptive. It's a reflected light off of whether or not the atoms, you need the atoms for the light to reflect off, for the light to actually be able to be pushed in one direction more, on one side more than the other side. One side can't push more than the other unless something changes in how the energy is absorbed and reflected. It's always absorbed and it's always reflected, technically. Stuff doesn't absorb the energy, it just converts it into some other form of energy and then re-radiates it, is really what the argument is. And so it's hard to get imbalances between those things, unless you design the experiment very carefully. So he went on to Newton's cradle.
Yeah, no?
Now the thing you can see is that these balls do move around, and that's part of how you can probably understand what's really happening. Because in this circumstance, when you're starting, only one of them has any momentum. And all the action has to come out of that original momentum. So everything else that happens can only be a reflection of the momentum. So anything in the opposite direction is clearly just going to be a type of reflection. So it's sort of like when we get pushed by gravity, the Earth technically doesn't push back. It doesn't create some new opposite reaction force. It's just taking your energy and just throwing it back at you. And that's it. Your energy makes both motions. The motion in was your energy. The motion out, any reflection by you, is going to be your energy just turned around and pointed back at you. It's just a reflection. It's all reflection. So you think of the kinetic balls bouncing back and forth. I guess I might as well draw it. I mean, I'm here. I have crayon-ish thing, chalk, so I might as well draw. So I would argue it's something like this, that the balls are under tension just because of the way they're stringed, so they tend to want to be close together. But when you crash one in, what it's really going to do, it's going to hit this ball, and then this ball is going to reflect a little bit of that energy back, and then that energy is going to reflect back this way again, and that's going to make this ball move. And so they're all doing that, and so each ball is basically catching energy and reflecting it back at the same time. Some of it's getting reflected, some of it's going straight through, but a lot of it's getting, at all kinds of points, it's getting reflected. And so these balls in the middle are really, it's like it bounces away, then hits the ball here, bounces back, and then it bounces this way, and then it bounces this way, and then it bounces this way. So it's jiggling here, back and forth. And this one jiggles. And the trick is, this one can't, right? Because there's no ball over here to hit it back again, so there's no reflection. So when it gets hit, it goes. And so what's really happening is, as it's leaving, as it's accelerating, this ball next to it is bouncing back and forth really fast. And so it hits it, and then it moves a little way, and then hits it again, it moves a little way, and it hits it again, it moves a little way. So it really hits, and then finally there's a distance it gets where this one can't hit it anymore. This one swings out, and it doesn't have any extra to hit it with, and so it swings back again. And that's the last they connect to each other. And that's why this one leaves before all the energy. If I drop two balls, all the energy hasn't gotten to this one yet, because this ball still was swinging and it didn't have a chance to hit it. And so it goes back, and then it gets hit again, and so this ball swings out. And eventually the second ball follows the first one. So you put 2 in, you end up with 2 out. But they're really, this one left first, and then this one leaves. That kind of thing. I think that's probably something like how it works. But it's all, the one momentum line has to create all of that. And that's why you have a little bit of losses, is because the other balls are still jiggling when the other ball left. They're still jiggling. That's why the thing slows down relatively quickly. I mean, they don't last, it doesn't last as long as it'd be better if it could last longer. So anyway, he doesn't really describe any of that. He just says something like, well, it has energy. You know.
Directionality to it, since it has this velocity squared term in here.
Okay, so I'm obviously arguing, I guess what I'd like this guy to address is can you ever collect this kinetic energy formula? Where can you ever collect the disproportion it creates? So if you have one object that's moving 12 miles an hour and has 1 unit of velocity, and another one's moving twice as fast and weighs twice as much, those 2 objects are supposed to have very different kinetic energies. The light one has twice as much, yet they have the same momentum. So my direct question is, do you have any experiment where you ever extract that extra kinetic energy? Is there any experiment you can do to prove that extra kinetic energy actually exists? Or that it's anywhere close to the actual total of how many joules of energy there actually are? Does this formula get the right answer? And I would argue it doesn't even come close. So, anyway. But that's the direct question being asked. So you don't have to watch the rest of the video. But I'd appreciate it if you did.
There's no more vector information.
Okay, the vector we know exists. Whether you play some game about your formula, we know the vector in reality exists. That the energy always has a vector. Momentum always has a vector. It can't have more than one vector. It can only have one vector. Things can only move technically in one direction. You know, you can break it up and pretend it has vectors in different directions, but technically, even if it had directions, even if it was actually moving in physically different directions, it would still add up to one vector of momentum.
So what we have to add is the momentum equation.
Right, well, there's no point in saying we have to add, because the number is completely different. I mean, it's a completely different number of joules, a completely different amount of energy. Doesn't get the same answer, except a few times coincidentally. You know, when the mass and the velocity are actually disproportionate to the equation in terms of their but it only gets the correct answer 1% of the time. Okay, so 99% of the time momentum will not give you the same answer as the kinetic energy formula, and that's a significant problem.
As you can see, it always works. There's always the same number of balls on the outgoing side as the incoming side.
And they always tend to want to maintain the same velocity, because the velocity is important, because a slow thing can't push a fast thing. So even the slow thing has 1,000,000 joules, let's say. I made it really heavy and it has 1,000,000 joules. It just doesn't matter if the slow thing has gone away from it, because you hit it and it now moving faster than the thing that has the 1,000,000 joules. The 1,000,000 joules can't get into the thing because the thing is already gone. It's already left the contact point. So contact is a key part of measuring how well you can transfer. You have no hope of transferring if you've lost contact with the thing you're attempting to transfer to. So the first rule is this inelastic and elastic crap has to relate to the fact of how long can you maintain contact. How long can you capture reflection? So even the train example with train couplers, locking. If people have seen that actually happening in real life, it jiggles like crazy. So when they hit each other, it bounces, bounce, 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 bounce. So the energy is getting reflected. There's all kinds of reflections going on, but because you have a coupler, you still have to force the energy, has to still go one way, because you've coupled the trains, and now all the energy has time to move in there. It moves in through banging numerous times into the other car, And it can only have the chance to do that banging because you didn't allow the reflections to be meaningless.
We can even try it with 4.
Okay, this is sort of not exactly useful, but I just want to get to the point where he...
In this demo, I'm going to show you...
Okay, so he switches to a new conversation without really explaining anything about how that energy was transferred or what the right way is to measure it. So I just wanted to point out I'm not I'm not eluding any of the important parts of this video. I'm just trying to, for brevity, just get to the basic point.
Momentum is conserved even if kinetic energy is not.
So again, so this idea that there's two kinds of energy or there's more than one kind of energy and that somehow you don't have the same obligation to conserve whatever the energy is, and that the only place you could put it is as potential energy, but there's no explanation for where it's hiding as potential energy, especially in the two train example. Okay, where you have where's in the heavier train moving slower, where is the potential energy? I mean, no, sorry, it's the wrong example. But that's the one you're saying it has energy, except it's not kinetic. It's hidden as potential. They have the same momentum. You're saying this item has half as much kinetic energy, and so the only place the other energy can be is as potential. Well, what do you mean potential? Potential of what? Doesn't have any potential energy, just has momentum.
Remember that total energy can't be created or destroyed, but we certainly can...
Right, so it doesn't make any sense for you to say kinetic energy can and then not explain where the kinetic energy is going. Because we know that any deformation, any sound, any heat, any of the things that are normal that we see, we know all of those will come out of the momentum. So when the other balls are vibrating and moving, we know they came out of the energy of the ball that's leaving. So, we know that's a closed system, so you just can't keep saying, well, the kinetic energy was lost to blah, blah. No, the momentum had to be lost to that too. You can't have heat, you can't have noise, you can't have sideways movement, you can't have distortion, you can't have deformation unless you take it out of the momentum. So again, this argument just fails to get to the real, to stay coherent. I mean, I don't have to conserve kinetic energy, but I do have to conserve total energy, and I do have to conserve momentum. I mean, it doesn't make any sense. How can this kinetic energy be special unless you're going to say there's potential somewhere, and then if you say there's potential somewhere, you have to explain where the hell it is, because there's no rational place to put it. Where's it hiding? Glove compartment? Where's the potential energy hiding?
Convert kinetic energy into something else, and that's what I'm going to show you right now.
So he doesn't do any conversions here at all, in the sense of you think he's going to, but he really isn't converting anything that you could see.
So I have two rubber balls here, and notice that they behave very differently. That one doesn't bounce very much at all.
So a hard one and a soft one. So I mean, this is going to be sort of obvious in terms of understanding what's happening.
And this one bounces quite well. So to investigate this a little further, I have a force sensor, a flat piece of plastic here that acts as a force sensor on this aluminum bar, and it's connected up to a sensing circuit, and that is connected up to the oscilloscope.
Right, so the implication is he's going to measure how much force, the momentum of the object. He's not measuring momentum at all. So that's the first thing to understand. He's just going to measure how much pressure for how long was applied to that piece of plastic. So it's just about how long the thing was in contact, pushing on it, more than how much pressure it pushed with. It's not able to measure how hard did I hit it. It's only able to measure how much time did I spend pushing on it.
I'll do another video talking about oscilloscope setups, but here we're just going to talk about the physics. And when I tap on the force sensor, you can see that the oscilloscope registers the force applied over time, and I've also set up the oscilloscope to provide the time integral. So the red line is actually the integral of force over time.
Right, and it's just really saying how long was the thing applying pressure on the surface. And it's not going to tell you anything else. So the longer you pushed on it, the more that line would go up. But it doesn't really have anything, so the shorter the tap, the lower the line. So it's just really, again, about how much pressure you're applying over how much time. And it really isn't going to be measuring what your absolute amount of momentum you're transferring.
So if I just tap it very lightly, you can see that the integral becomes a steady state value, and that corresponds to sort of the total amount of force over time.
It really doesn't correspond to the actual amount of momentum or the amount of energy the object actually has. So again, if it was to measure trains this way, it would fail also.
So let's drop each ball on the force sensor and see if there's any differences in it.
Oh, cool. My camera is not working. I should have noticed that, but I did not. Oh, this is a little bit irritating because it doesn't scroll, but whatever. That should fix it. Appears to be fixed. Oh, sorry about that. It's hardly very important.
Graphs they produced. I've set up my desk lamp here so that I drop them from the same height, and it's centered right over the force sensor. So we'll start with the non-bouncy ball. Okay, and
so we know that that's not too very good at an experiment he's doing here, because we don't get to see if it hit the middle of the sensor, the edge of the sensor, not too perfect. So it turns out the one that doesn't bounce is a little bit heavier, 20% heavier, he says. So the rubber ball, the super ball, is lighter.
You can see that the value, the red line, is leveled off. Now let's try the bouncy ball. As you can see, the red line is quite...
So it's this big, giant line, and you can kind of know intuitively that doesn't make too much sense, because the hard ball obviously delivered all of its momentum to the surface pretty effectively, and it only had a little tiny line, you know. And this one clearly didn't deliver much energy at all, because so much of the energy ended reflecting so quickly. So the momentum wasn't in the surface very long. Or it might not have even gotten to the surface, which is the more important argument.
A bit higher, indicating that there was more force applied over time to the bouncy ball.
Right, so he's saying there's more force, blah, blah, blah. You know, this isn't really a velocity, equation, so that's part of the problem. I mean, obviously the heavy ball did travel faster. I mean, they both have the same velocity, and what we want is an experiment where they have opposite velocities.
Now, hold on a sec, you might be saying. Maybe the two balls don't have the same mass. And actually, you'd be correct. But as it turns out, it's the non-bouncy ball that's about 20% heavier. So the heavier ball actually had a lower force applied to it in this test because of the momentum transfer. So with the bouncy ball, we had this momentum coming in, and after the bounce, after the contact, it came shooting back off this metal plate. Therefore, there was more momentum imparted to the ball by the table, the metal block, and the earth. So
again, he's saying it was imparted by those things. But again, it really wasn't. It was just reflected. So you only have one momentum vector in the equation. The table doesn't have any. The sensor doesn't have any. It has no vectors. So there's only one vector that everything has to come out of. So everything that happens has to come out of that momentum vector. I mean, everybody should be able to agree on that. That shouldn't be even debatable in any sense at all. This should be like, yes, of course, that's what it has to come out of. So if the ball bounces, it means it had to get its own energy reflected back at it. So I guess it might as well just start talking here. I might as well. He's not going to illustrate it that much. I'll play it, but I mean, he's not going to really get into a very deep explanation of exactly the mechanics of what happens when two different kinds of things hit a surface. So I would argue clearly over time, if you did the experiment a lot of times, what's going to happen is that the hard ball is going to make a dent, in this table. And the soft ball will never make a dent in the table. So that'll be one evidence that one is actually putting its momentum into the table, and the other one isn't putting its energy into the table. So the rubber ball will do that first, I guess. So you can sort of understand that if I'm going to measure how much contact there is, if I'm going to have a timed sensor that's going to sit there and sense, how much time is this in contact with this, that's already going to be a huge prejudice to this rubber ball, because what's the rubber ball going to do when it hits? Well, it's going to compress, so we know this is what it's going to do, right? It's going to flatten on the bottom, and then the outsides are going to bulge, and this is what the rubber ball is going to look like, something like that. Well, what's happening when that's happening is well, first you're, spreading the energy over a larger surface, so now that's giving plenty of opportunity for the energy to come in such a way where it can reflect back to the surface, because it's going to be, as you spread the energy out, you're essentially slowing it down. So now the energy doesn't get really deep, it doesn't go shooting into here real far, because I've made a bunch of little pokes instead of one big poke. You can sort of understand that, right? The energy is now in a form where it can be dissipated over a lot of atoms, So I'm poking a lot of atoms a little bit instead of poking, a few atoms really hard and pushing them really deep. So the energy is now reflecting and reflecting and reflecting and reflecting and reflecting and reflecting. And the energy that's going this way, we know the ball is going to push that energy back this way. So like a wave popping up into gravity, gravity is going to push the wave back down technically. And that extra pressure is going to give the wave energy to go the other way. So we know that this is the high pressure now, right? Because there's a lot going on here. There's reflections fighting against pressure coming down. So we know this is the highest pressure, and that any of this energy that's going to bounce back this way, because the ball wants to get back to its original condition, it's pushed a bunch of energy out this way, and that energy is essentially now going to reflect back. The ball is going to go back to its original size, and it's going to push that energy this way. So all that energy is lost. It won't go into the ground. It won't go down. It's going to go back up. All right. So all of the energy that was diverted sideways is now going to go back out, up. So it never even hit the surface. Some of the energy from the top of the ball that's now compressing, it's getting flatter. As it fell down, it flattened. Well, you can sort of understand that this reflecting energy back up is essentially going to hit that energy, and that energy is going to reflect out too. So that energy that now is going to reflect off its own reflection, the reflection of the bottom of the ball is going to reflect into the ball, and it's going to basically reflect the energy of the top of the ball. So the energy on the top of this ball never even gets to the target, because it's essentially going to bounce off the reflection, and it never even got there. Okay, so it's it never even got to the ground. So half of the ball's energy never even got into the ground. The ground never even felt it. Okay, so that's what I'm going to argue. It never even felt it. But there was contact with the surface for quite a long time, because all this takes time. All this, bending and distorting and, rubber banding. That all takes time, so there was lots of time. It was in contact with the surface before all of this reflection turned into motion in this direction. So very little of the energy actually got lost into the surface, because it only contacted the surface in this gentle way, okay? And all of the energy, you got half of it back, let's say. All the energy that pushed in, you got at least half of it back in the opposite direction. So that's why the ball retains its energy, doesn't lose it to the surface, because it made the contact really easy to reflect. It kept the energy on the surface where all the energy could reflect back really easy. All right, and then the opposite case of the hard object, the unyielding one, it hits the surface, and all the energy has to go through this tiny amount of mass on the surface, and obviously it creates very strong amounts of momentum, atoms moving, stuff moving, so it ends up going very deep, okay, and now it starts dissipating, because some of it's going to reflect, but it's going to dissipate a lot, and it's not going to have much chance to do any of that. But there will be some reflections, and so we'll have just enough energy just to say, I'll just go over here. It'll pop off a little bit because it gets a little bit of reflected energy back, but it's a tiny percentage of the energy. So the energy goes deep. It can't get back to the surface to push the ball far, and it ends up dissipating as it's coming back out. It doesn't go back out at the same speed, so it's obviously just like the bullet. A bullet goes in, cuts a really nice hole, but you could understand if the energy had to get back out, it wouldn't be such a good hole. It's going slower, and it's going to tear and rip things. That's basically what's going to take place. So you got all this weight, you lost it all to heat, and you're certainly going to cause, because you are impacting the surface over time, you're going to dent this surface. The surface is going to dent because you are deforming it too. So there's real permanent deformation that'll be part of your loss of energy in just bulldozing all of these atoms into new places. So that would be the real argument, and none of it has anything to do with any, 1/2 mv squared. There's a certain amount of energy in the ball. It's represented by its motion and its mass, And anything that happens at the moment of impact, anything that moves, heat moving, deformation moving, any movement of anything has to come out of that momentum vector. There's no other vector to take it out of. That's it. There's no such thing as kinetic energy. There's just momentum. And there's no place to hide potential energy. You either have it in terms of, chemicals, or you have it in terms of gravity. But there's no potential that you can hide inside of the object, inside of it as motion. That's just nonsense. That goes over here, and so we'll continue. But I've sort of contexted the argument. He's really not measuring the real energy. He's not measuring how many joules this thing really has. He's measuring a certain amount, a certain way of transferring energy. And as those two rubber balls demonstrate so obviously, clearly how the energy is transferred makes a huge difference in terms of how you're going to be able to measure it. If the ball takes back with it 3/4 of the energy, obviously you're not going to be able to measure that energy because you can't keep it.
And that required more force to be pushed into the ball, whereas the non-bouncy ball came down and stopped, and there was a very small rebound, which means that less force was put into the ball to push it back up into the air.
So less force was pushed into the ball. Again, less was reflected. All it can do is reflect. All it can give you back is the energy you pushed in. I mean, it really is that simple. I mean, yes, you can think of it in terms of, well, you dented the earth and that pushed stuff out and it did all. No, but the earth is just going to reform. It's going to go back to exactly the same energy it had before you hit it. It's not going to give you some kind of extra energy. It's going to give you exactly what you did to it. It's going to go back to its original state. So it's going to be a net zero, okay, before and after, technically. And except if you deformed it permanently. So unless you did these deformations or some other thing, it's going to give you back the energy as heat or as something else. And that's all there is. There's just the momentum the ball has. The earth doesn't provide any counter energy. It either reflects your energy back into you or it doesn't.
Now the masses are pretty close, and so dropping them from this height means that both of these have about the same kinetic energy when they hit.
Well, I mean, 20% is not pretty close, and especially, when you have an equation that says the mass is half important. So then you end up with it's 40%.
And yet one of them had more momentum coming out. So where did the kinetic energy go? Well, the non-bouncy ball converted it to heat. The bouncy ball retained most of the energy. It came in with about the same kinetic energy as it left with.
So it really didn't. Okay, it's not about the same. It's at least 20% of a loss, something like that. But regardless, blah blah blah. The point is, it either retained its energy through a reflection, either a reflection inside of itself, like it's like, if you hit the ground, you could theoretically think that your stomach is going to go push down onto your feet when your feet hit, and then your stomach's going to bounce back off your own feet, pushing up. I mean, it's just a reflection.
But the non-bouncy ball, converts it mostly to heat. And so if we did this experiment 100 times or maybe even 1,000 times.
So again, it's not mostly, I mean, you could say mostly heat, but I'm sure deformation is a big part of it. It takes a lot of energy to move atoms of wood, to new positions. So the deformation is probably 50% of the energy is just in deformation.
We would notice that the non-bouncy ball is slightly warmer after doing this because it's converting more of that kinetic energy.
So again, the ball will get warmer, but also the table gets warmer. So you have to measure the heat in the table, and the heat in the table is probably going to be more substantial than the heat in the ball, because the ball really isn't elastic, and it really can't hold energy, and it really can't do any of that stuff as readily. So there's probably going to be a lot more heat because of the direction arrow. The momentum arrow was in a direction, and obviously it's more readily going to put the heat in the substance that the momentum arrow is moving in that direction, and less likely to put it in the ball. So the ball won't get nearly probably as hot as the table got.
heat. And another clue, you notice that the sound of impact is different. The non-bouncy ball has a much sharper, louder impact sound.
Yeah, well, that obviously just has to do with whether you're going to trap air, but I mean, in the two circumstances, who knows how much air velocity was actually produced by the two circumstances of squishing, deforming and shaping to the surface, probably displaced more air, so more air volume was moved. But the truth is, the hard thing when it hit, it might have created some X-rays and some gamma rays and some other kind of stuff because of the intensity of the energy transfer.
Gives you another clue that more energy is being converted from kinetic energy into something else, in this case sound waves. Another thing to notice is that in the bouncy ball case, the incoming speed was about the same as the outgoing speed after the collision, and this is a consequence of how the momentum rules work. So if you...
Well, see, that really isn't. It's just that you have obviously less momentum, so you can't change its mass, so of course you have to change its speed. I mean, the obvious way you're going to measure a loss of energy is in velocity, because you can't lose the mass. In this circumstance, losing mass won't be a very reasonable explanation for a change.
If you've ever seen a rubber ball bouncing out into the street and then hit by a moving car, you'll know that the ball actually comes off from the car faster than the car was going. In fact, it will be about twice the car's speed, because the car is much more massive than the rubber ball. And so all of that momentum transfer will go into the rubber ball, and it will actually be going twice the speed. It's just how the equation comes out.
Yeah, I don't know if it's exactly twice, which is the tricky part of that one also. But clearly it's not 4 times, and just has to do with how well the ball is accepting energy over a period of time. So the more elastic it is, the more it can stick to the car for a longer period of time without leaving. Alright, so the more it can mush into the car, cover a larger surface area of the car, and then release, then the faster it's going to be able to release.
However, remember that motion is relative. So if you're standing on the street, it looks like the ball is going twice as fast as the car.
Well, motion isn't just relative, but whatever. It's also absolute. You can have, there's nothing theoretically wrong with the idea of having both absolute space and relative space. You can certainly have absolute shared motion, and then you can have relative motion in the context of that absolute shared motion. So the two are not in conflict at all.
However, if you're in the car, it looks like the ball was approaching you at a speed that is half, and then after the collision it's receding away at a speed that was half, is what you would observe on the ground. Okay, so now we know that a bouncing object,
if you're looking at it from sideways,
will impart more force to the thing that it hit, and that's because momentum is conserved. And so if this object is coming in and hits the table and then bounces off, that means that the table did more pushing in order to get this.
Alright, so again, the table really didn't push, it only reflected. So that would be the first argument, is that you're just certain things have time to reflect, and when they have time to reflect, you're going to get the energy back. If you leave before if the energy has reflected, then the energy is going to end up dissipating in the surface that you left. The momentum stuck in the thing you hit if it doesn't have time to reflect it back at you.
Moving in the opposite direction. So remember, it's a vector quantity, so if this is considered the negative direction, and now suddenly it's going positive, then...
Alright, so again, there's no such thing as a positive and negative momentum, so even if they have opposite momentums, they don't cancel, they have to go somewhere else. So again, bogus argument in my opinion. Bogus as a statement, it doesn't saying the truth. There's no such thing as positive and negative momentum. All momentum is positive, and if you have it in the opposite directions, it still has to go somewhere. It's still going somewhere. It just won't be going left and right. Instead, it'll be going up and down or forward and back.
There had to have been an equal amount of force from this other object, the earth, the table, everything in this room, to push it back the other way.
So again, it doesn't push back. So that's just, I probably said things like that too, and it's just not actually correct. It just either reflects it has time to reflect it back, or it's stuck with the energy because it didn't reflect it soon enough.
Knowing this, an inventor came up with a clever way to make water wheels more efficient. So,
all right, so this is sort of a different subject. I'm not saying it's not interesting, but it's kind of basic physics also. And it's this whole argument I was making about, if you're already moving and, energy is moving different speeds, that you always have to have a differential in your speeds. If you're moving the same speed as something, it's very hard to transfer any energy. So you have to have differential speeds, and obviously any idiot can know if I concentrate the water onto a certain, so it all hits you instead of missing you, or being able to go in other directions, that obviously you're going to get more energy out of it if you don't just turn it, but you also force it to reflect. If you can get the reflection to go backward, okay, then you're going to have to interact with the entire piece of the energy. But the reflection obviously is coming back at 0 energy relative to the object, so the object's motion is what's going to be created out of the energy.
Requires more force. Now,
so you can sort of understand
Let's
that.
zoom in on just this part of the pump.
Like I said, obviously this is just really saying that obviously buckets work much better on a wheel, a water wheel, because then the water can't do that sneak around thing. So the idea is to create a mechanism that empties and fills the bucket. Empties and fills the bucket, so the bucket constantly catches all the new energy. All right, all the action in one direction. And it doesn't give anything back in the opposite direction. So it keeps the entire momentum. The momentum goes in, and it doesn't reflect. Even though you're obviously pushing it back, it's not a reflection. You took all the energy out of it, and you gave back something not moving at all because you moved. All right. The water has no pressure after it goes through the U-turn. So even though he drew it indicating it's sort of shooting it back out, it's really not shooting it back out, because it's shooting it back out at no velocity. So it absorbed all of the velocity. So obviously it's just a way of saying, look, you can make a water wheel more efficient by not letting the water splash and go sideways. All right. So that's a different subject. I don't think we really need to go in that. I think it goes back to the light subject, and it just doesn't get to the key point, that the conservation of energy is in this context of you having two different ways of measuring energy, momentum and kinetic energy, and those two ways don't get the same answer, and that's really a big problem. And that's the question you really should address, is how can two things have the same momentum and yet have very different kinetic energies? And if there's no place for potential to be hiding, there's no theory for how you converted kinetic into potential, how can they have different kinetic energies if they have the same momentums? How can they have different total energy? And they can't, is the simple answer, and there's no experiment you can create where you'll ever collect the energy of the kinetic energy formula, because it's not real energy. That's the assertion. Not even close to real energy. I mean, it's so bad at guessing. It's so bad at predicting the actual joules of energy that you could extract from the object by extracting all of its energy. The water wheel will do a better job. I can change the velocity of the water, and you'll find that you can't get 4 times the energy by increasing the speed of the water, okay, twice as much. If I increase the water speed twice as much, I'm not going to get 4 times the spin out of the water wheel. It's not going to happen. Alright, so that's enough of a video, I believe. So, till the next time and such. And, it'd be really nice if I could get one of these smart people to actually answer one of my videos. But I'll just have to hope.